Hello everyone. In the past couple of sessions, we have been looking at implementing the linear regression model by only considering a specific sample set. The sample set that we have considered involved only 6 different observations and 3 different columns of variables here which is associated with X data. So with X and Y data that's given to us, we looked at implementing the linear regression model, which essentially is a single neuron model here. So this particular neuron had 3 different inputs that are received, which are x1, x2, and x3. These are 3 different variables that we have seen in the sample data. It also had a bias term associated with it. These are your model parameters. The weights associated with these different inputs and bias associated with this neuron are going to be the model parameters. We have implemented the gradient descent process in order to understand what could be our right values for weights and biases. And this here, the output here is going to be the predicted y values, or we can call it as yi hat. So z here is going to be summation of I equal to 1 to j w transpose x xi plus b. It's going to be sum of all of the weighted inputs that you are having plus this additional bias term. Since we do not have any activation function, or we can say that we have an activation function which is going to be a linear activation or an identity function. So whenever f of z is going to be z itself, then we call it as an identity function or a linear activation in case of neural networks. Since f of z is going to produce z itself, so this equation is going to be the predicted y values. So this resembles more of a linear equation that we already have studied during our machine learning and statistics, right? And hence we call this single neuron model as a linear regression model. So whenever I'm trying to extend this particular single neuron model to a multi-layer perceptron, it will no longer be a linear regression model. It's going to be a regression model, a generic regression model, since we are introducing non-linearity in the presence of hidden layers. So whenever you are considering multiple hidden layers like this, so this is my hidden layer 1, this here is going to be my hidden layer 2, and this here is going to be an output layer. So we have multiple inputs. So this is x1, x2, x3, and so on till xj. So we have j different input variables that we can associate with this particular network. And whatever output that each of these neurons would produce from any given hidden layer are going to explain the non-linear aspects of your X data. Let's say that we are using ReLU activation function or a sigmoid activation function. That essentially means that you are bringing in non-linearity here. So whenever your hidden layers are going to explain the complex non-linear patterns of your X data, it's no longer going to be a linear regression model. That does make sense, isn't it? Even if your output does have a linear activation function, even if there is a linear transformation of different outputs that the preceding layer is going to generate and being considered as inputs for this particular output neuron, even if this here is going to be purely sum of all the inputs that it's receiving from its preceding layer, we still consider the overall model here as a non-linear model itself, because there's already non-linearity that's introduced in the form of hidden layers here. With this as a context, now we are going to extend our discussion like in solving this particular regression problem by considering whole of the Boston housing price data. Earlier, we have restricted ourselves to considering a specific subset of the data where your Y data was the housing price data. And now we are going to consider whole of the data. So we already have loaded this particular data by reading this particular CSV file in our previous session, right? Now we are going to consider this X and Y data, which corresponds to n different samples that are present within the dataset. We are essentially going to create a multi-layer perceptron model where you are going to generate predicted y values. Later, we are going to assess what the loss could be, and finally look at implementing the optimization process as well, where we identify the right values for your weights and biases defined within your network. Without any further ado, let's look at defining a custom class called MLP, which extends this particular parent class called nn.module. So within this particular class definition, we are going to have an init method which will contain self and different parameters that we can define. Currently, I'm not defining any parameters as such, but we are also going to look at initializing the parent class by considering MLP and self within the parenthesis of super. And then we are supposed to invoke init method of parent class by using .init. Cool. So we also would want to define the different parameters here. The different parameters for MLP architecture could be the number of inputs or the number of neurons that you would consider in your hidden layer 1 and number of neurons that you consider in hidden layer 2, which are represented as H1 size and H2 size. And finally, what could be your number of outputs here? So within this particular init method, we'll also define the different layers that form this multi-layer perceptron architecture. So the first layer here is going to be hidden layer 1. So hidden layer 1, for creating this hidden layer 1, we are going to make use of nn.linear function. So nn is the module that we have tried to import. nn is going to help us create the model object, and optim here is going to help us create the optimizer object. So we are going to look at implementing the stochastic gradient descent or mini batch gradient descent in order to understand or in order to derive what could be our right, weight and bias values for the given network where you are observing minimal loss. Okay. So nn.linear basically would accept two different arguments. So one of which is going to be the number of inputs that this hidden layer is going to receive and the number of outputs that it's going to generate. The outputs could be the total number of neurons that you are having. Okay. So H2 is going to have the number of neurons that are present within the previous layer or number of outputs that the previous layer is generating, right? Which are considered as inputs to this subsequent layer. And finally, this also would produce a specific set of outputs, which I'm defining by H2 size. And we also have an output layer, again is going to be nn.linear. This here is going to receive the number of outputs that we observe in previous layer as inputs here. And the output here is going to be out size. So we are all associating this particular H1, H2 and H3 layers that we have created to the object itself by referencing self dot for all of these objects. Cool. So once we have defined the constructor or init method here, we're also looking at creating this additional method called forward, which accepts the X data. So now X data is input to this particular hidden layer H1. Okay. And this is going to generate an output called Z1. I'm bringing in non-linearity by applying ReLU activation function to all of these neurons within your hidden layer H1. So similarly, your subsequent hidden layer is going to generate outputs as Z2, but this time around, it's going to consider the preceding output as input here. The preceding layer's output, which is Z1, is being considered as input for your H2. Cool. So output here is going to be the predictions. So the predictions are actually generated from the output layer again, which is self.output. So the input for the output layer is going to be the output from the preceding layer, that is hidden layer 2, which is Z2 here. I'm not defining any activation function. It's going to be the same. Even if you're not defining any activation function, it's necessarily implying that we have used a linear activation, or the activation function here is an identity function. So we are going to return the predictions, and whatever class that we have now created, I'm going to instantiate this particular class and call the object as model. This particular class would expect all of these inputs. So the total number of variables that are present within my complete data set is going to be 13. We have 13 different X variables within our data set, and I'm going to provide 100 different neurons for my hidden layer 1 and 50 different neurons for my hidden layer 2. So these values here are purely arbitrary. Okay, you can experiment by changing these number of neurons that we expect for hidden layer H1 and hidden layer H2. Okay, I'm leaving it as an exercise to you in order to identify what could be the right values for H1 and H2. The out size here is always going to be 1. We only have one single neuron that's present within your output layer, and hence I'm providing this particular argument value as 1 here. So before you actually create this model object, I would want to recreate the data loader object, because we always need the X data in order to conduct this forward propagation process here. So whatever data set that we are having, whatever data set object that we are having is basically created by using this custom dataset class that we already have created. Okay. So data loader is going to help us get some sample data by using iter function. So next here is going to be, this here is generator object. It's going to generate pairs of X and Y as and when we keep running this particular statement again and again. Okay. So now we have a sample data that's defined for your X and Y. The number of observations that are present within X is purely dependent on the batch size that we have tried to supply as argument here while creating the data loader object itself. So with whatever X data that you are having, we're now going to implement this forward propagation by invoking this method associated with this object called model. We're also passing the X data and considering the output into predictions. So before running this, I would want to convert this X data into floating point data so that we're not observing any errors as such during the whole run process. Once we have generated the predictions, we're now going to define the loss function. To define the loss function and calculate loss. Calculate loss as well. Loss function is going to be the mean squared error. We are going to use this particular function called MSE loss and provide the arguments as the predictions that we have derived in the previous step and the actual Y values that we already have sampled from the given data set, the Boston housing price data set, right? So we can call it as loss. Loss.item is going to produce what is the total MSE that we have computed from the predictions that we have generated using the model. So the total loss that we are observing by considering only 11 observations as your input data is 581.51, which is way higher, right? So this is not the loss that we are expecting. And this is a high loss for the reasons that we are completely aware of, because we have not considered the complete data and we only have considered or conducted one single iteration here. We have not yet completed the iteration as such because we have not done the backward propagation yet and we have not updated the weights and biases as well, right? Let's continue with the process and later see how we can reduce this particular loss. So now let's do the back propagation by invoking backward function. So once the resultant gradients are computed, so we are now going to update this particular weights and biases by using weight update equation. So we're not going to write the whole equation like we have done in the previous session, but rather we are going to make use of this optimizer object that we are going to now create. So optim is a module that we have imported already. So we are going to use this stochastic gradient descent function, which expects the model parameters as input along with a particular learning rate value. For now, I'm providing an arbitrary learning rate value, which is 10 to the power of minus 3. So once we create this optimizer object, I'm going to invoke this function called step function. So step function is going to update all the weights and biases in the network. So we need not explicitly update the weights and biases like we have done earlier. So step function is going to take care of all of that. If you observe carefully, we have not initialized the weights and biases as well because nn.linear function is going to take care of the weight initialization as well. So this is one of the primary reasons on why we basically use these PyTorch built-ins itself for creating complex models, because we need not explicitly go about updating the weights and biases within the optimization process or model training process. And before we begin with the model training process, we need not initialize these weights and biases as well. Okay. So that's one of the good and primary advantages that we gain by using these different PyTorch built-ins that we are currently looking at. Okay. So once we run this statement, all the weights are now updated. So in order to check what the current weights and biases are, we can always reference the state dictionary by using model.stateDict. So model.stateDict is going to generate a dictionary which comprises of these different tensor objects associated with different hidden layers. Here, this particular tensor object is going to represent the weights within hidden layer H1. This here is going to represent the biases within hidden layer H1, so on and so forth. So it's going to produce what the weight and bias values are in the complete network at any given point in time. So this state dictionary is going to change in the next iteration because you are going to update your weights and biases again based on the gradients that you compute in the previous step, right? So that's pretty much all I wanted to discuss with you. So we are going to extend this particular discussion that we generally have now in our next session and try to implement the whole model training process. So we have not looked at implementing the whole of model training process yet. We only have considered discussing one single iteration so far. But one important step we already have forgotten, which is to invoke this particular function called zero grad. So zero grad is going to avoid cumulatively accounting to different weights and biases that you must have computed in all of your previous iterations. So we do not want PyTorch to cumulatively add up all the gradients that are computed in multiple iterations. So initializing or probably zeroing out all the gradients is one of the critical steps in the model training process. Okay. So we have multiple steps that we have implemented so far, one of which is going to be creating the data. And then we created a model object, and using this forward method, we have generated the predictions. We also have looked at what loss is, implemented the backpropagation where all the gradients are computed, and then we actually updated the weights and biases within the network by invoking this step function, which points to the SDD process that we have implemented with a given learning rate here. So learning rate, number of epochs, all of these different parameters are hyperparameters within the model. So please always remember the difference between model parameters and hyperparameters. So model parameters in this particular context is going to be weights and biases that you are trying to find the right values for. Hyperparameters could be your learning rate, the number of epochs, etc. Right? Or batch size. The batch size that you are defining for each iteration is also going to be one of the hyperparameters that you necessarily look at finding the optimal values for. So we are mostly going to discuss about hyperparameter optimization in one of our upcoming sessions. But in the implementation of this multi-layer perceptron regression model, we're all looking at finding what could be the right values for weights and biases, where we are observing a minimal loss, right? So minimum possible loss is what we are necessarily going to look at. Okay. So that's pretty much all I wanted to discuss with you in this session, and see you in the next. Thank you.